Welcome. So today we want to continue our discussion of homeostasis, and in particular we want to look at the regulatory mechanisms that allow the body to maintain homeostasis. And our learning objectives are going to be, first, that we're going to contrast reflex and local homeostatic control. Secondly, we want to define the components of the reflex loop. Third, we want to explain negative and positive feedbacks, which are regulatory loops that are used to control homeostasis. 4, explain tonic and antagonistic controls. And then 5, we want to explain circadian rhythms. And this is going to give us an overview of all the mechanisms that we're going to deal with one by one within each individual organ system. Each system has a specific method that it's going to use to maintain homeostasis. So all of these will not be common to all of the organ systems, but that each system, for instance, will use a specific type of control system. And so as you go through the course then, you'll be able to come back and look at this lecture and recognize the specific concept or specific mechanism that's being applied. Okay, so what are we talking about with homeostatic controls? So first of all, we have homeostatic controls that's affected at a local level. And this local response then is occurring with neighboring cells. So the first is we have cell 1 and we have cell 2. And the cell 1 secretes a chemical, and this chemical then acts on cell 2, which has a protein or what's called a receptor, which can bind the chemical and become activated by the chemical, and it just gives it a response. This type of control is called a para-control, where one neighboring cell is governing the actions of a second neighboring cell. We can also have a system where cell number 2 is secreting a chemical where that chemical feeds back on itself and regulates itself, its own activity, and that's called an autocrine control. So we will see these autocrine controls and the paracrine controls, in particularly when we're looking at the gastrointestinal tract. We also have, for local controls, what are called gap junctions. And with gap junctions, the two cells are physically connected. There is a bridge between the two cells, and this bridge is called the gap junction or nexus. This little opening, which is common to the two cells, allows ions to flow from one cell to another. And in particular, we will see that we can move calcium from cell 1 to cell 2, and that this will occur within the cardiovascular system. It allows the entire, all the cardiac muscle cells to act as a single sheet so that they will all contract in unison and all relax in unison. And it'll be dependent upon the amount of calcium which is being delivered across the gap junctions and to all the cells. So those are going to be our local responses. But for most of the course, we're going to be talking about the reflex loops. The reflexes or the reflex loops are where the response is made at a distance from the target cell. And the target cell is a cell that can respond to whatever the signal is that's being released. These cells, the cells that we're talking about, are all the cells of the body. There's some billions of cells within the body, and we have to be able to have the cells communicating with one another so that they can have an organized or regulated function within the body. Two major communication systems are the endocrine system and the nervous system. And that's what's diagrammed here. So in the endocrine system, we have a cell, which is the endocrine cell, which secretes a chemical. And this chemical is secreted into the bloodstream. That chemical is then delivered by the bloodstream to cells which have receptors on them. That is, proteins on their surfaces or internal to the cell, which can recognize the chemical. And these are called the target cells. So the endocrine cell is then regulating the activity of the target cells through this secreted chemical. In the case of the neuron, we have then a cell which actually butts up against the second cell in an area which is called the synapse. And this is a very, very small space. The neuron will secrete its chemical into this small space, and this chemical is called a neurotransmitter. The chemical will act on the effector cell, that is the second cell in the series, and this cell could be a neuron, it could be a gland, a cell from a gland, or it could be a muscle cell. Whatever this cell, the effector cell or target cell is, it has a receptor which can recognize the chemical that's being released by the neuron, and then it binds to this receptor and causes the effector cell then to have some change in its activity. In both the endocrine cell and the nervous system, what we're governing is our cells at a distance from the originating signal. And so they're called reflexes. So if you recall, the last time we met, we said that the reflex loops had specifically 3 components. The first was a sensor that recognizes the stimulus. So we have some kind of an input which is coming into the body. So this is called an afferent path. It's an inward path to the body. And this sensor detects that specific signal and then sends that information to the integration center, which is the second component in the loop. And that's going to be usually the brain. And this is where we have our set point. So the brain already has a set point within it that then examines the inputting signal and evaluates whether or not it is higher, the same as the set point, or lower than the set point. If it is different from the set point, then the integration center sends out an efferent signal. This is an efferent path or a path that's going outward from the integration center. And it's to the effectors. And the effectors are what's going to cause the response. And this response then will take care of the stimulus. And in most cases, the response eliminates the stimulus. And under those conditions, this will be called a negative reflex loop. And we'll talk about those in just a few minutes. So let's just consider, just in general, a case that exemplifies these reflex loops. And the first of this would be we have an external change to the body. So the body, now you are leaving your room and you're going outside and it's snowing outside, and so it's very, very cold. And as you're standing outside and you don't have a coat on, your body starts to lose heat. And as it does so, its temperature will drop from 37 degrees, which is its normal temperature, to, let's say, 34 degrees Celsius. So as the body is cooling, then these signals are being sensed or are being detected by peripheral thermal sensors, which are present along the skin and also within the body along the core, where it's detecting the temperature of the blood. So we have both these peripheral thermal sensors as well as central thermal sensors, which will then send the information to the brain, to our integrating center, and this in an area called the hypothalamus. This area has a set point for body temperature, which says that the body temperature should be 37 degrees centigrade. And obviously, the input signal is 34, which means that the body is cold. The integration center, or the brain, recognizes the body is cold and sends out an efferent, along an efferent pathway, an efferent signal to the effectors. And in this condition, we have multiple effectors. One, we have skeletal muscle. Skeletal muscle will start shivering. It contracts and relaxes and contracts and relaxes. And as it's doing so, when you're shivering, you start to generate heat. The second is that on the blood vessels, which are perfusing the skin, the blood vessels which are directly underneath the skin are then the blood is constricted and is removed from that area to a deeper portion of the body or deeper portion of the skin so that we do not lose as much heat from radiation. So we have vasoconstriction. Vaso meaning blood vessels are constricted, and we're moving blood away from the surface, right underneath the surface of the skin, into a deeper layer of the body. So we don't lose as much heat then from the body through the skin. In addition to that, we can curl up so that we actually decrease the amount of surface that's radiating heat. And then obviously we can turn around and go back in the house, put on a coat, put on a sweater, and then go back outside, or stay in the house where it's nice and warm, and the body then will warm up. The effectors then are going to generate heat. So as they increase heat, we will eliminate our stimulus, which was that the body temperature was low, and bring the body temperature back up to normal, which is 37 degrees. Exactly analogous to the thermostat, which is within your house. But what about internal changes? So we can also have an internal change. For instance, you get an infection, and this infection will activate a cell called the macrophage. The macrophage secretes a chemical which is called a pyrogen. And the pyrogen acts on the hypothalamus, the same area of the brain that was active when we were having an input from the thermoreceptors on the skin when we were outside in the cold. This area of the hypothalamus, where our original set point was 37 degrees, but in the presence of the pyrogens, the set point is now 40 degrees centigrade. The body is now, the set point is 40 degrees centigrade, but the input stimulus, which is coming back to the hypothalamus from the skin and from the core temperature of the blood, is saying that the body is at 37. And so the brain then interprets the body as being cold. It will send out an effector signal to the effectors, which are, again, our skeletal muscle. The skeletal muscle will start to shiver. We will have contraction and relaxation to generate heat. And we will have the vasoconstriction of moving blood then away from the surface, underneath the surface of the skin, into deeper areas so that we do not radiate as much heat. The consequence is that we generate heat. The body starts to warm, and as the body starts to warm, it then is moving from 37 to 40 degrees. It's exactly the same reaction that we had when we were going outside in the cold. The body is responding in exactly the same way. The difference here is that the set point has been reset. And this is an important point to remember, because often when the body has a pathological condition, it is trying to do something which it normally would do to rectify a situation. It may be, in fact, responding to a set point that has been set to a higher level. And so that's actually causing a malfunctioning within the system itself. All right, so most of the reflex loops that we're going to be talking about throughout this course are going to be these negative feedback loops, or feedback loops which remove the initiating stimulus. The negative feedback loops can be simple, and that's what's diagrammed here, where the stimulus is received by, for instance, an endocrine cell. That endocrine cell secretes a hormone or a chemical which works on the target cell and then removes the stimulus, the initiating stimulus. So what do we have an example of this? So you just finished lunch, and as you finished lunch, then you ate a lot of rice, and the rice has now been digested by the gastrointestinal tract, and so glucose the amount of glucose that's within the blood has risen. So an increase in plasma glucose levels then will cause an increase will act on the beta cells of the pancreas and cause the release of insulin. Insulin is a hormone which acts on the skeletal muscle, and it makes the skeletal muscle take up that glucose into the skeletal muscle, removing it from the blood so that it's taking it into the skeletal muscle for storage. And as it does so, then the plasma glucose levels will fall. Okay, so we are removing then the initiating signal. The negative feedback loops can be also very complicated. And this we'll see when we talk about the hypothalamus, pituitary, endocrine feedback loops. For instance, that's what's shown here, where we have a stimulus, and the stimulus works on the first cell. This cell secretes a chemical A, and that chemical works on the second cell, B, which stimulates the secretion of the chemical B. And it then works on C, which then eventually works on cell D. And there is a negative feedbacks to each of these levels, so that each level then is turned off by the stimulated chemical. So do we have an example of this? Well, temperature. So again, we have a system where we have our temperature of the body is falling, and when temperature of the body is falling, then the hypothalamus, the brain, will cause the release of a hormone which is called a thyroid-releasing hormone. And this hormone works on the pituitary, another region of the brain, which releases thyroid-stimulating hormone, which then acts on thyroid hormone gland. This gland will secrete thyroid hormone, and the thyroid hormone acts on all the cells of the body to increase the metabolism of all the cells of the body. And in doing so, then, it revs up the generation of heat. So this is a simple, this is a very complex reflex loop, a negative reflex loop. But again, by generating heat, we then remove our initiating signal, which was low temperature. Now, in some instances, we will see positive feedbacks. Positive feedbacks don't occur in very many locations, but we will see this in the female reproductive tract, for instance, where we will have an instance where the cell is going to we have an endocrine cell secreting a hormone called follicle-stimulating hormone, which acts on the target cell to increase the receptors for follicle-stimulating hormone on that target cell. So all of these follicle-stimulating hormone receptors then increase in number, making the target cell very, very sensitive to the FSH. So that's one way to have a positive feedback, where you're increasing the sensitivity of the target cell. Another way to do this is that we simply have the first target cell then secretes something which causes more of the initiating signal to increase. And this is what's characteristic of the clotting system in your blood. So that when we start that cascade is a cascade of proteases. And these proteases then feed back and activate themselves so that you have an accelerating system. So you get more and more and more and more and more of the fibrin clot. Obviously, you don't want the entire bloodstream to clot, and so there has to be a way to turn off the positive feedbacks. And the way to do so is through a negative feedback loop. Now, there are a couple more things that we want to consider, just very briefly, and then when we come to them within the organ system themselves, we'll talk about it in more detail. But the systems that we've been talking about up to date have been things where we turn something on and we turn something off. But under the condition of tonic control, now we're just modulating the activity of a specific cell. We're never really turning it off and we're never really turning it on. And a tonic control is exemplified by the smooth muscle cells, which are lining around the lumen of the blood vessels, such as your arteries and your arterioles. Under normal conditions in the body, those cells, those smooth muscle cells, have a basal state of contraction so that the lumen of the vessel is not completely open or completely closed. And that's what's shown here. That's our basal state. If I increase the sympathetic nervous system activity to these smooth muscle cells, I can cause the cells to contract. And when they do so, they will make the lumen of the vessel much smaller. So they will decrease the size of the lumen. And that's through increased input from the sympathetic nervous system. So this is called vasoconstriction. Vaso for the blood vessel, constriction. We are causing contraction of the smooth muscle, which is around that lumen, and making the lumen smaller. I can decrease the input from the sympathetic nervous system, and by doing so, then the smooth muscle cells will relax, and then the lumen of the vessel will then open. And this is called vasodilation. Vaso, again, meaning blood vessel, and we're dilating. So we're opening the lumen of the vessel. So if you notice a couple of things. One is that we're not turning on or off the system at any one time. We're simply modulating how much activity we have from the sympathetic nervous system. And the second thing is that we have a situation where the smooth muscle can hold a specific state of contraction for very long periods of time. And there's this tonic, long held contraction, which is unique to smooth muscle. We couldn't do this with skeletal muscle, and you can't do this with cardiac muscle. But with smooth muscle, you can hold the contractile state for very long periods. So this is called tonic control. And the tonic control, one way to think about it is thinking of a radio dial where you can dial up the volume and you can dial down the volume of the sound, but that you never actually turn it off. Now, in the body, we also have antagonistic control which is mediated by the nervous systems. And we have essentially two types of peripheral nervous systems to deal with. One is called the parasympathetic, and the other is the sympathetic. On the heart, we have input from both the parasympathetic and the sympathetic. And the two nervous systems are going to work in opposite directions, or in an antagonistic manner. They are not binding to the same receptors, but they are working in an opposite control. The parasympathetics are going to slow the heart rate, so that if a normal heart rate is 100 beats per minute, that's our intrinsic heartbeat, then the parasympathetics will slow it to less than 100 beats per minute. This would be what you would see with a very highly trained athlete. Somebody like Lance Armstrong, for instance, they could have a heart rate that's 35 beats per minute. I have a heart rate that's 80 beats per minute. So 35 beats per minute is a very, very low heart rate. They have a very high parasympathetic tone. We also have situations where we need to increase our heart rate. So if we start running or we're going swimming, we have to have a higher output of blood from the heart. We have to increase our cardiac output. And that's going to be by using the sympathetic nervous system. And under these conditions, we can increase our heart rates so that we go above 100 beats per minute. So we're stimulating the heart to increase it. And as we talk about the cardiovascular system, we'll describe exactly the mechanisms by which these two nervous systems are able to control a heart rate. And then the last thing that I want to talk about is our circadian rhythms. Circadian rhythms are where biological systems in your body are changing on a 24-hour cycle or 24-hour basis without any input from you. This is on an automatic, rhythmic kind of a situation. When you go to sleep at night, for instance, your body temperature will drop. And then when you awaken in the morning, it will rise again. And the drop is only a couple of degrees, but while you're sleeping, you have a lower basal metabolic rate, and body temperature will fall. The other one that we see that's regulated by biorhythms or by circadian rhythms are hormones. And so we have two hormones that is diagrammed here. One is growth hormone. Growth hormone is released during early sleep, and then it falls to more basal levels when we're waking up. Well, cortisol, a second hormone, increases, well, just before you wake up. Cortisol and growth hormone are both activating glucose levels. As you're sleeping, you have fasting, and so blood glucose levels can fall. And these two hormones are raising blood glucose levels. The growth hormone raises the blood glucose level by having a signal coming from the empty stomach, which is another hormone called ghrelin, and it turns on the secretion of growth hormone. The growth hormone raises blood glucose, and then cortisol also comes on and raises blood glucose further. And this very high blood glucose level actually turns off the growth hormone signal. So growth hormone is regulated by low, it's turned on by low blood glucose, and it's turned off by high blood glucose levels. So these circadian rhythms occur without us thinking about it, and you're all very familiar with them. For instance, when you are traveling, then you move from, let's say you're going from New York to London, you go through time zone, and when you arrive in London, then you're 6 hours off from your normal time zone. For about 2 days, a day of 24 hours to 48 hours, you feel a little odd. You feel a little off. You're hungry when other people are not hungry. You want to sleep when other people don't want to sleep. And then eventually your body sort of gets accustomed to the time zone that you're now functioning in. What has happened is that your body has reset the set points. So they reset the set points for the circadian rhythms. And when you reset the set points not only for temperature, but also for cortisol and for the growth hormone and for all of the other factors which are being governed by the circadian rhythm. And it takes a little while for the body to reset the set point. And what resets the set point is sleep-wake. These are cycles which are dictated by sleep-wake and not by light-dark inputs. So what about people who are known to be night owls? And what about people who are early birds? What do I mean when I'm talking about night owls and early birds? Are you a night owl or are you an early bird? Night owls are those who can stay up all night long. They've got plenty of energy, and at 4 o'clock in the morning, they're about ready to go to bed. But they certainly have a hard time to wake up at 8 o'clock in the morning, because when they wake up at 8 o'clock in the morning, then they feel cold, they can't think very clearly, they're looking for their coffee, they can't find their shoes, so they're off. They're not happy. The early bird is the converse. The early bird wakes up at 5 o'clock in the morning. They're ready to go. They're full of energy. Their body is warm. They want to find their coffee. They find their shoes, everything, and they're out and running. So the difference between these two, these are both normal people, but the difference between them is that their circadian rhythms are different. So circadian rhythms can vary depending upon an individual, and they're not necessarily pathological if you are a night owl or if you're an early bird. I have a good friend who lived for many, many years in Seattle, and he has now lived for something like 20 or 30 years in Durham, North Carolina, which of course is a different time zone, and he has yet to change his circadian rhythm. His circadian rhythm is still based on Seattle time. All right, so what are our general concepts? So the general concept is, first, we have stability of our internal variable is achieved by balancing our inputs and outputs to the body and among the organ systems. Second, we have in a negative feedback system, the change in the variable is corrected by bringing the body back to the initial set point. However, the set points can be reset, and this is an important point. We can reset them when we're resetting our circadian rhythms, but we can also reset them to tolerate higher sodium within the body, or to tolerate lower temperatures, or to tolerate lower blood pressures or higher blood pressures. So these set points then are modified. And then thirdly, it's important to remember that it's not always possible to maintain everything relatively constant. There's going to be a hierarchy in the maintenance of life. And again, the brain is going to win. The brain wants blood, the brain gets blood, and it will shut down the circulatory system to perfusion of all the other organs. The brain and the heart, okay, win. All right, so the next time we come in here, we're going to talk about some more about the balances of these fluid compartments and how we move materials from one compartment to another. All right, see you then.